I want to tell you about the math behind Q-learning and SARSA. I will go backward, starting from Q-learning and SARSA learning roles themselves, and then going backward to the history from where they come, and then I start from the root and go forward again to reach these two. In the previous lecture, we talked about two problems, maze and the cartwheel, in both of which we had to repeat many episodes to have a good Q table. A Q table was the table which was used in the test phase for decision making, in which we had states and actions in the form of rows and columns. So each row corresponds one state, and each column an action. Each cell is the value or reward of taking that action in that state. And it was called Q table because it is a quality table. It shows us the quality of taking action, let's say A2 in state A1, and that quality was recorded here as a numerical value, and that value was our reward. And we had to update this value many times. Updating means learning, means training. So how was that training done or learning done? By overwriting our previous, if existed, our previous reward. So you had a reward here, and you would observe the same state, you would take the same action, but this time the reward would change because now you have more information about your word. That information doesn't include just the current observation, but also your guess about the future. Your guess comes also from the Q table. It's like that: I'm going to travel to somewhere, I will read about it, and I guess how good it is to go there. From where do I have that information? From the past of other people, but it is my future. So the information that I have about my future, because in reinforcement learning we talk just about future, but the information that I have about the future that I don't consider completely as correct information because the word changes, but that information is recorded somewhere. Some people have written it, and that text could be interpreted also as, let's say, Q table. It's not a Q table, but it's a quality measurement tool. Quality Q table. So we want to overwritten the rewards. So we had a reward recorded here. Using a Q function, we got access to that reward. We wrote it again and then added something to it. That something was regulated by a learning rate, which was a number less than 1. If it was small, it means that we would take the previous value and add a small number, a small value, and a small numerical value to it, because we would calculate something here and reduce that by multiplying, let's say 0.1. We would take just 10% of this and add to this. Yes? So what was that something that was the base of our updating? It was the immediate reward. This was immediate reward. It means this is not what I have read about the past of the previous people, which is my future. It is exactly what I see now. I am in the airport. I choose an airport. Is the airport good or bad? I arrived to this airport. So I took the taxi and went to there, and I see if the airport is good or bad. I see it. This is immediate reward. Okay. And then I had something else being added to this reward. Yeah? Something else being added to this reward. For now, close your eyes to this. We don't see this. Yeah? We don't see this and this. These two are different in Q-learning and SARSA. These two are different in Q-learning and SARSA. Let's for now imagine that they don't exist. Let's imagine that they don't exist. Let's concentrate just on R, the immediate reward, and on Q, which was the recorded reward. The recorded reward of taking action A in state S. Let's concentrate on just these two. You see a subtraction. Subtraction is difference. Yeah, subtraction is difference. That means that if what you had recorded in the past is bigger than what you see now, result of subtraction will be negative. If what you have seen in the past is smaller than what you see now, the result of subtraction would be positive. It means that either you have a positive, I say, forget about this, it doesn't exist now. Either the value that you have here is positive, that means something will be added to your Q value or to your previous reward, or it is negative, it means that something will be subtracted. So this is this part of the story. But we know that we took the action A in the state S, and we have arrived already in a new state. We want to update the value. How good is this? How good is this? We want to update this value. How good was taking action A while being in state S? And we know that we should also consider the future moves. Yeah? Consider the future moves. It means the moves from the next state, state S prime, the next state on. Which action will we take from here on, or after being here? If you look into the character of your agent, you know your agent. The agent is a small child. You know that after the small child arrives home, he will study or not study. You know your child, for example. If you are realistic, you may say, I know that he will go and watch cartoon. Then I evaluate this way of sending the child alone home. So I took a taxi for him. He arrived home, a positive reward. Yeah, he's already in front of the home. But from then on, which action will the child take? Are you realistic? You would say that the child will watch cartoon, and then you evaluate. So it was good to send the child home with taxi. He has arrived, but he will not study, right? With a high probability. He may also study, we don't know. But with a high probability, he will not. So the fact of sending a child home with taxi, if you want to evaluate it, you may reduce the reward. You may not give the best reward. You would get the reward of taking the action watching cartoon to the child, to the movement, to the action of sending him with taxi. It's good, but at the end, what will happen in the next state? This is when you are realistic. You take the reward of being in the next state, taking the next realistic action. You are just imagining this state. I mean, this step is not being taken. You are imagining, because you are updating the value of the reward of the action that you took right now in the previous state, and you're updating that. You have not taken the next action. You are just imagining. You're just thinking. So you take this reward of the next state, and the next state, you multiply a discount factor to it. That tells us how important is the future. If this is a small number, it means that that value will be reduced. If it's a big number, it's never more than 1. Then we consider the future rewards strongly. Yeah? So this is when you are realistic. You are in Sarsa. You think about the character of your agent. That character in the literature of reinforcement learning is called policy. It is a policy. Yeah? But you may be too positive and say, I know that the child would do, I don't know, just sleep, eat, or watch cartoon and will not do his homework. But anyway, I will be positive. When I want to evaluate sending the child with taxi home, I would consider the best thing that will happen after that. The child will arrive home and do his homework, will study. Yep. So you iterate over all actions that the child would take, watching cartoon, eating, sleeping, or doing homework. See which of them is better. You consider that to go to your Q table, retrieve the value, and then multiply to discount factor, and then apply it to this formula. I mean, consider it as a part of this formula. So you have the immediate reward, you had the previously recorded reward, and you have a portion of the future reward. And this all together either increases your Q value, your reward of taking action A in state S, or decreases it. And how much increase or decrease comes from this alpha, and also from how big the discounted future reward is. So this was the difference between Q learning and Sarsa. So it talks about updating the rewards, and the difference between them was that, are you realistic when you go to the next step, when you want to choose the next action to update this reward, or actually the reward which is here. Are you realistic? You look at the policy, or you consider or you imagine the best action. This is next state, and this is the next action. So this was the story of Q learning and Sarsa. Okay. Let's go one step back to the history and see from where Q learning and Sarsa have come. You see two formula here, two equations here, one here, and I have written them under Sarsa and under Q learning. You see that there are similarities. For example, here we have a max, here also we have a max, here we don't have a max, here also we don't have a max. We have this discount factor, and we have state and action, and these are also can be rewards. So let's hack them, see, break them, see what these notations mean, and then try to understand these equations. Actually, this equation is from where Sarsa learning rule comes. This equation is the root of Q learning rule. So you see in both equations we have a P here which stands for transition probability. What is the transition probability? Transition probability is the probability of landing in state S prime by taking action A in state S. This is probability. It means that you send the child from, let's say, school to home by taxi. Taxi is an action. You could send a child by bus or bicycle or walking. Yeah? This is taking an action, which means using a taxi from the state of school. Yeah? With a high probability, the child will arrive home, but there is a probability that there will be an accident, or the child will tell the taxi driver that I want to go to my grandmother. So the same action may end in different states. Let's say with high probability the child will be in the state of home, but the child can also end up in other places. So this is the probability, transition probability. Transition means going from one state to another state. This is a transition probability. In both formula, both equations, it's the same. We have a pi. In the equation which is written under SARSA, this pi stands for policy. Policy is the character of our agent, character of our, let's say, the child. You see, this is also like transition probability. This is also a conditional probability. It's a conditional probability. What does that conditional probability tell us? It's the probability of taking an action in a state. The child is in the new state, S prime, the child is at home or is the home of grandmother. What is the probability that the child will study or watch TV or eat or sleep? Yeah? So this policy is based on the character. Policy is the character of our agent. And we have probabilistic agents. They may act differently being in the same state. But we have a probability. We have a good child with the probability of 95% will sit and study, or another one who with the probability of 80% will just watch cartoons. Right? So this is the policy. You see, here we don't have a policy. Q learning is off policy. SARSA is on policy. Yeah? The SARSA uses a policy for predicting the future reward. It was realistic. Based on the knowledge about the agent, we decide which action the agent will take in the future. In Q learning, we used a max. It means that we consider the best possible action that the agent would take. So it means that here we don't have a policy. While thinking about the future, here we consider the policy. So now that we understood the notation here, let's pay attention to something else. Here in Q learning and SARSA, these Qs are given access to a table. So this is a table is being used. Yes? This is a table, a memory is being used. This is a function, is a dynamic programming approach that we update a table. Yeah? We update a table. These Q functions that we have here, actually they give access to a table, a memory. Here we are not talking about a table, we are calling a function. Yes? This function is calling itself by new inputs. And this function also is calling itself by new values. So we have a recursive call here, recursive call. So actually our Q learning and SARSA learning rules are a modified version of these two equations in which we use tables but not recursion, not stack, let's say. So this is an improvement. So for, let's say, for implementation. So SARSA and Q-learning come out of these equations they use tables to make our implementation efficient or practically implementable. Yeah? Okay. We have two equations which are the roots of SARSA and Q-learning, and they are recursive. Okay, let's now look into this formula equations, see how they work. In both of them we have the immediate reward. It means that the reward that we observe, we don't read from anywhere, we observe the reward of taking action A in state S, and we take that reward and directly add the discounted future reward to it. The discounted future reward is directly added to the reward that we observed right now. But what is the discounted future reward? This is discounted by discount factor by gamma. So you take each state that may happen by taking action A in state S. You calculate or look up the probability of that state, and then from that state, you iterate over all possible actions. For each action, you consider the probability of that action being taken based on the character of your agent, the child. So the probability of watching TV, the probability of eating, sleeping, or studying, and each of them has a value in your head, has a reward. Then you multiply the probability of that action to the probability of to the value, to the reward that action will bring. You add all of them together. It can be that just one action is possible. This would be equivalent to just having the value of that action in the future state. Yeah? So this was for the time that we consider a policy. We are realistic. Okay, now let's go to the situation where you are optimistic and you consider the maximum possible reward from the future state. So how do you act? You consider all possible future states, consider their probabilities. So it means that you say let's say state of being at grandmother's home, how probable it is by taking a taxi from the school. You multiply that probability to the maximum reward that the child would take from being at grandmother's home. It means maximum reward, for example, studying. Yeah? You iterate all in your head over all things that the child would do in grandmother's home, and you choose the best action that the child would do, and then you consider the reward that you would take from that action, and you multiply it to the probability of that action being taken by the child. It can be that there is just one probability, one action probable. That means all probabilities are 0, and just one probability has one action has the probability of 1. Then this would be equivalent to just simply the best reward that you can take from the next state. Why do we sum? This is the sum of rewards of being at home, being at grandmother's home, being kidnapped, being at friend's home. So these are the sum of all of them. Why do we sum? Because they have different probabilities. We are not actually adding all of them to each other. It can be that just one of them is possible. That's why this sum has a meaning. This sum, without this probability that gives us the weights of each state happening would be meaningless. Yes. So now we have SARSA, we have Q-learning, and two equations from which SARSA and Q-learning come. One of them is called the Bellman expectation equation. One of them is called Bellman optimality equation. Optimality comes from the max, expectation comes from the policy. Now you have two equations from where the SARSA and Q-learning come. These equations are recursive. So actually these are the same thing, but instead of recursively calling a function, we are using a memory and we are updating values. Here we have also by definition recursion, but practically we don't have recursion. We use these formulas many times, these update rules many times, overwrite our values, but we don't have recursion. Okay, everything I said till now and everything that I will tell in the future about reinforcement learning will be, and it was, it is, and it will be about the future. It's never about the past. It's never about the past of an agent in the current life. Even if we refer to the past, it is the past of the agents which have already finished their job. Let's say if I'm going to travel and I read a recommendation, it's correct that the recommendation is written in the past, but it is not in my past. It is someone else's past. It's my future. I want to go somewhere tomorrow. I read a text about this journey, which is written last year, to guess my future. It's about the future. It doesn't matter from where I come. It matters now how to reach the future goal. Yeah? Mathematically, it can be written like this, that the transition probability of moving from state T, means current state, to the future state, to the next state, state T plus 1, this probability is equal to the probability of being in all past states, including the current state, and then moving to the future state. It means that you consider them or you don't consider them, it doesn't matter. You see, this part is missing here, and the probabilities are the same. If you have such a condition, you say that your problem has Markov property. Markov property, it means the past doesn't matter. The only information that we need to decide about the future is information about the current state. If the problem has Markov property, then you can solve it by a Markov decision process. Markov decision process is the process of making decisions in such situations when you take the best action, the action that brings you the best reward, just based on the information about the current state. So this is the Markov property. In order to solve a problem of Markov decision process, we can use two equations. You can use Bellman optimality equation, or you can use Bellman expectation equation. These were recursive implementations. So recursive, or this is a recursive way of thinking about them. So Bellman optimality equation, Bellman expectation, coming implementations of them. One of them is Q-learning, and one of them is SARSA, which are implementation. So Bellman optimality equation is related to Q-learning, Bellman expectation to SARSA. Okay, let's review. If you have a problem which has Markov property, you can explain it using Markov decision process. If the environment is not predictable, you have to be realistic, then you can explain your solution using Bellman expectation equation. If the environment is reliable, is let's say deterministic, you can explain your solution using optimality equation, Bellman optimality equation, in which for guessing the future reward, you choose the best action, the best possible action. Then if you choose optimality, the implementation will be Q-learning. If you use choose Bellman expectation equation, then the implementation will be SARSA. So this was the fast introduction to the mathematics behind Q-learning and SARSA. In the next lectures, we will go deeper, and we will also look into different corners of the reinforcement learning. And hopefully see you soon.